All right, so I say recall because that's what every textbook in creation says when they want you to remember some important rule. The binomial theorem. So NCX, so a combination, n things taken x at a time, p to the x, 1 minus p to the n minus x power. All right, the Poisson distribution allows for extremely large values of n and extremely small values of p. Right, so since mu equals np is the mean of the binomial distribution, we can use it as a way of scaling up or scaling down, depending on what we're looking for. The idea is that for large values of n, things can get out of hand probability-wise very quickly. So if what we do is use a normal binom PDF and say, all right, the n value is like 1,000, that's automatically going to scale us up into extreme parts of the binomial distribution, and we'll always end up getting obscenely small values for probabilities. But what we can do is transform our binomial theorem so that instead of just looking at n, we're looking at how individual values, x values, compare to the mean. All right, so basically we're shifting the entire binomial distribution up away from 0 as its center and centering it around a new value which is associated with the mean. All right, so we could actually arrive at the Poisson distribution using this technique. So all I would have to do is just make some substitutions based on this relationship. All right, so mu is equal to np, which would mean that n is equal to p over mu. All right, we could also solve it for p, in which case p would be equal to mu over n. All right, so with some substitutions, I could say nx, a combination of n things taken x at a time. Instead of p to the x power, I'm going to say mu over n to the x power, mu over n. And then instead of saying 1 minus p to the n minus x, I'm going to say 1 minus mu over n, and the n could be thought of as p over mu minus x. Oh, actually, we could just leave that as n. I could change it later. So we'll say n minus x. All right. So this actually is the basis of the Poisson distribution, right? Just this substitution, this simple substitution, right? What we want to do is allow for extremely large values of n. So what we do is we find the limit as n approaches infinity of this whole shabiggity bang. All right. So, just a little background in pre-calc is all you really need to be able to handle something like this. And also knowing what the general definition is of a combination. N things taken x at a time. Yeah. Formula for that is n factorial, so I'll just color code this somewhat. So we got this guy here. That's the same as saying n factorial over n minus x factorial times x factorial. All right, so that's right out of your notes. No, you can't help you. Not with this. This next piece I could break up. Mu to the x power, n to the x power, write it separately. And I could also do something very, very similar with the last piece. So I'll do that in green, I think. Just keep the score at home. All right, I could break that up because whenever you have a sum or a difference in the exponent of an expression, it's really the result of an operation performed on the expressions. So was it keep the base, add the exponents, or in this case keep the base and subtract the exponents? If that's the case, then prior to this it must have been division. So 1 minus mu over n to the nth power, and 1 minus mu over n to the x power. All right. So that's keep the base, subtract the exponents, but in the reverse order. Oh, my colleague's in the back. All right. So not really doing anything crazy here. Yeah, it's like all like first week of calculus. Yeah, based off of your study of limits. In my calculus classes, I don't even really go over this too much. It's more like, here's some examples involving properties of limits now see what you can do with it, you know? And so those in the calculus classes know that that's true. I mean, I will say we've never done anything as crazy as this, but the skills are still there. One thing that we learned in calculus and even pre-calc is that anything that's unrelated to the variable in the limit doesn't need to be contained within the limit. All right, so the limiting constant, or the limiting variable in this case, because infinity would not be considered constant, is n. So anything that does not directly contain an n does not need to be within the limit. All right, so let's pull them out. So I could take out the x factorial. Let me just smidge it over a little bit so I can get my highlighter to work properly. X factorial can go away, mu sub x can go away. Everything else in some way, shape, or form or another has an n in it, and so we'll have to account for that. So let's at least get those out of the way. Now, if you're flipping through your packet and looking at the Poisson distribution formula, you'll see that this is actually a key component of it. All right? So the only thing we're really missing now is e to the negative mu. So somehow all of this remaining stuff needs to amount to an e to the negative mu. And you look at this and say, oh, okay, I don't see how that's going to happen. But it's actually pretty cool how it does happen. All right? So limit as n approaches infinity of all of the remaining ingredients. But I'm going to keep them as separate fractions. So n factorial over n minus x factorial. And then the other stuff, well, that's a different conversation. We have to do something kind of crafty with that. All right, so let's focus on...
Where n to the x go?
N to the x? Good question.
The red fraction.
Yeah, it should still be there. I missed it. So times 1 over n to the x. All right, so let's focus on one fraction at a time. The first one is easy enough to handle. You might look at the last one and say, well, wouldn't that make this whole thing zero out? Well, conceivably you might think that, but there's a workaround that we're going to be able to incorporate into this. All right, so the blue fraction, let's take that into account now. So that's what I'm going to focus on here. So we're looking at the limit as n approaches infinity. Now this limit applies to everything here, so I want to be absolutely clear about that. Just because I'm boxing off this part doesn't mean that we're not applying a limit to the remaining stuff. I'm only focusing on that first piece. All right. So n factorial could be written, if we write the expanded form, as n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 times n minus 6 times, well, anything that you can think of all the way down to 1. All all right? But along the way, and this is the interesting part, along the way, we're going to have an n minus x, an n minus x minus 1, an n minus x minus 2, an n minus x minus 3, and so on. All right? Whatever that x value is, that's going to be part of the journey that I'm going to encounter all the way down to 1. All right? So I'll just put the last entry as a factor of 1. The reason that's important, and I can show you numerically in a second what I mean by this, because I think, you know, notation-wise, it's a little iffy. It's like, okay, he's just making stuff up. But numerically, it'll actually make a lot of sense. But on the bottom, we're going to have an n minus x minus 1, n minus x minus 2, all the way down to 1. And all of this stuff is going to cancel. So we would just need the value that was prior to n minus x. All right, we'll account for that in a second, but let me just take you through a numerical case real quick. So let's say I had 10 factorial over 10 minus 8 factorial. All right, so this is my n, which corresponds to that n, and this is my x. All right, now 10 minus 8 is 2. That's my n minus x, right? If I were to detail out the entire factorial, 10, 9, 8, all the way down to 1, this one would just be the 10 minus 8 factorial, which is 2 and 1 multiplied. All right, so this is n minus x, and this one is n minus x minus 1. All right, so that corresponds with these entries here, which end up canceling out. It doesn't matter what values I choose. If I did 10 factorial over, I could even do 100 factorial over 100 minus 8 factorial. All right, if I did that, what I'd be looking at would be 100 all the way down to 0. Obviously don't want to write all that down. But then here this would be the n minus x factorial, which would be 92 factorial. So 92, 91, 90, and so on. All right, so what this is telling me is that I really, if I have 97, 6, 5, 4, 3, 2, everything after that, well, actually everything starting with that last entry is going to be irrelevant because it's going to cancel. All right, so these are numerical instances that are coinciding with this notation. But the thing is, again, I need the numerical value that precedes that canceled value because I need to know where this is going to stop. All right, but for now, I mean, you could kind of consider, well, maybe it's not going to be too necessary because if I rewrite this as limit as n approaches infinity, and now I'm going to bring back in the n to the x. All right, that's going to be my denominator because my denominator canceled out completely. I would have n times n minus 1 times n minus 2 times, let's say you didn't even consider the fact that I needed the value that preceded the n minus x, you could still kind of figure it out because on the bottom I have n to the x power, which is going to be n times n times n times n, as many times as there are x values. All right, so making separate fractions out of that is going to help us come up with a limit n over n times n minus 1 over n times n minus 2 over n times whatever. Because ultimately this limit's going to end up equaling what? Not negative.
0.
Not 0. if it was 0, everything would cancel out. What's the next best number?
Negative infinity.
1.
1. All right, because if you remember your limit rules, if the powers are the same, we find the ratio of the leading coefficients. So ratio of 1 to 1, 1 to 1, 1 to 1. In each case, we're getting a 1. Multiply all those ones together, you get a result of 1. All right, so what that tells me is that all of this stuff, the factorials and that n to the x, they're just going to cancel out. All right, so you're just like, whoa, we did all that just to see that it cancels out. Well, yeah. And it was fun. Honestly, kind of think about it. If you think about what we're aiming for, we're aiming for a formula that's got a mu to the x power, an e to the negative mu power, and an x factorial in it. I already got the mu to the x, I got the x factorial. Wouldn't this stuff have to go away? Right? Because this all has to pare down to e to the negative mu. The only place where I have a mu is in this area here. So this stuff would necessarily have to go away. This is really just a justification for it. All right. So now we have to actually make some more things go away. So this is where we're at now. So the limit of a quotient is the quotient of the limits. So I could take these two expressions and find the limits of them separately. So I'm just going to focus on those. Now they're different enough that we have to use two different approaches to find the limits. One approach is actually going to be to use our knowledge of exponential e. So that's where we're going to focus our attention for the first part. But the second part, that's just evaluating a limit. There's nothing really to it. So we'll actually tackle that part first. So I'm just going to get a common denominator. Limit as n approaches infinity. Common denominator would be n minus mu over n to the x power. One of the properties of limits tells us that if you have an expression contained within a limit raised to a power, you could find the limit of that expression and raise the result to that power. When you think of it that way, it's actually pretty easy because we know mu is some constant multiple, so it's a number. It's an ugly looking number. Mu is mu. I mean, you look at it, you don't, the number 2 doesn't jump off the screen at you, but it might as well because it's just some constant. So I'm not worried about that. If I take the derivative, oh, sorry, I don't want to get too far ahead of myself. If I use the same technique that I used here, power relationship, I get what? I get a 1 again, all right? For those of you in BC, so this ends up being a 1, and so the bottom ends up canceling out. You could use another technique. It involves a derivative. Have you learned L'Hopital's rule?
I knew you were going to say that.
Yeah. So you would just take the derivative of top and bottom, you get 1 over 1, and then you're done. You know, so, and that would have applied here, it would have applied previously, it would have applied everywhere. All right, so what that gets me to is the idea that that bottom part was even irrelevant. All right, so somehow this component here has to come out to give me a result of e to the negative mu power. All right, so that's what we're going to kind of discover now. And it's kind of an interesting workaround. So limit, I'll do it in purple. Limit as n approaches infinity of 1 minus mu over n to the nth power. All right. So a rule from Algebra 2 and Pre-Calc that you've definitely seen before. It's just a question of whether you spent a lot of time, whether or not you spent a lot of time with it.
Well, the definition of E is 1 minus the limit as n goes to infinity of 1 minus 1 over n to the n, right?
1 plus. So the rule, limit, I'm going to change the variables up here because we're already using n for something, but the limit as a approaches infinity of 1 plus 1 over a to the a is equal to e. All right, we can verify that on our calculators. When you were learning about compound interest, exponential growth decay, continuous growth and decay, things like that, this concept should have come up at some point. It's just a question of how much time was spent on it. All right, so my function, I just put it in as 1 plus 1 over x to the x power. And very simply, all you'd have to do is go into the table and just start scrolling. And you'll see that as you scroll up towards positive infinity, it does appear like the y values are leveling off at a particular number. And that number is in the neighborhood of about 2.7-ish, 2.71. Eventually it settles on 2.718-ish, which is the approximation for Euler's number. All right, so you can get it that way. All right, so the question becomes, well, how is this useful here? Well, it has the same structure. All we have to do is redefine this so that it follows the same model. So what I'm going to do is I'm going to take the bases of the two exponentials and set them equal to one another. Oh, and by the way, during this process, you start to really understand just how friggin' smart this Poisson guy was, right, to have come up with all this stuff on his own, right? Because, like, there were no graphing calculators back then. So, I mean, this is definitely in the realm of cool math. Not like that stupid website called Cool Math, but cool math is in math that is cool. So if I can figure out the a value here that transforms my purple limit, purple math is also a thing, purple limit into the form of the red limit, then I'm good to go. All right, so the ones will cancel. And so I have negative mu over n is equal to 1 over a. And so I could solve for a. And I can also solve for n. And I would need both of those pieces of information. So a would be equal to negative n over mu. And n, just through cross multiplication, would be equal to negative a times mu. All right. So I'm just using substitution here. I'm going to replace pretty much everything I have. I mean, if I want to, I could just replace the n and let everything simplify out, but I could also replace the negative mu over n with a 1 over a directly. That's the easiest way to do it, because if you replace just the n here with a negative a mu, it'll eventually simplify to just give you this relationship 1 over a, so you kind of spin it over for nothing. All right, so we have limit as not n anymore. The limit as negative a mu approaches infinity of 1 plus 1 over a, not to the nth power anymore, but to the negative a mu power. Right. The limit itself, the constants on the bottom, I mean, if you're looking at negative a mu But if it were ever able to get to infinity, then we would have a relationship negative a mu equals infinity. But that's more theoretical, but we could actually consider that. Because I really want to know what's happening as a approaches infinity. So I would divide both sides by negative mu. And what would infinity divided by a negative constant be equal to? Negative infinity. So we redefine our limit as a approaches negative infinity. We have the 1 plus 1 over a. I'm going to write it to the a power, and then raise that whole shabiggity bangity boom here to the negative mu power. The rationale being that what's contained within the limit should give me a what? Limit as a approaches negative infinity of 1 plus 1 over a to the a power. What should that give us?
E.
E. So we have e to the negative mu, which is ultimately what we were looking for. So therefore, our shortcut rule for the Poisson distribution we take all the other components that we had like an hour and a half ago, mu to the x over x factorial, so it's up there, right? I mean, we factored that out immediately, so you don't want to lose sight of that, multiplied by the e to the negative mu, over x factorial. And so that's your probability of x.